So let me make up a story where we use this concept of at least one. So let's look at the probability that you throw a dice and you get the number 5. Would you all be comfortable with the probability of throwing one dice and the number 5 comes up is going to happen 1 out of 6 times? Agreed? Now, we've talked about independence, correct? One event has no effect on the next, right? So suppose you throw 3 dice in a row. What's the probability then that they're all a 5? Well, that can use a rule called the multiplicative property of probabilities, which really just means you can multiply them together. In this case, 1/6 times 1/6 times 1/6. Now, on your calculator, isn't there a button that will do this a little bit quicker than actually multiplying it 3 times? Does anybody know a different way of doing that single calculation?
You can cube it.
The cube.
Yeah. So you raise it to power 3, you cube it. Now, that could be really useful if it was, 8 5s in a row. Don't you want to just do it in one big go rather than a 6 times a 6 times a 6 times 6? Now, when I put this together, it's going to be ridiculously small, which is fine. And I'm rounding this answer off to 4 decimal places, and that would be it. Hold that thought. We're going to do something over here that's going to help us do another question in a minute. If you have a thing, let's call it A, and its probability is 0.3, there's another guy called AC. That's the complement, right, of A. And won't that be 0.7? You remember doing the guy and the opposite thing of the guy, right? So A is the event and A complement is the total opposite of that, right? Now, if I ask you for the probability that all 3 of the dice are 5s, which is essentially that, all of them are 5s. What is the complement of that event? And we have to be a bit careful here. What is the opposite? All 3 of the dices are 5.
All 3 of the dice are not 5?
Didn't you say last on Monday
Yeah.
that only one of them needed to be a 5?
At least one is the word. Right. So it's at least one is not a 5, right? So the complement of all of them being 5 is at least one is not a 5. Okay. Are we cool with that? Right. So if I went and said to you over here, what's the probability at least one of them is not a 5, wouldn't that be the complement of this event? So I can simply just subtract this guy from 1 and get 0.9954. So do you see that if I know one event, can I get the complement of that event without having to do any any messy multiplications or whatever? Are we good with that idea? That the complement of all of them being something is at least one of them is not that something. And that's essentially the sentence that we're going to be working with here. Right. How about this one? I'm trying to find one here. Yeah, this is a high school story. Right? So this is question 14. I know I'm jumping around a little bit, that's fine. In question 14, and this person goes to a high school, and once a year in October, they have a homecoming day. And the probability that it rains on any given day is 0.23. So the probability that it's dry then, would you agree that's 0.77? Are we good with complement? Right, it's rain or it's dry, right? And we're going to be asked some questions to do with, and remember it's a 4-year deal, right? So once a year they do it. So the first question is, what's the probability it will not rain? So I've already answered that, it's 0.77. The second question is, what's the probability it will not rain on any of the homecoming days? So it doesn't rain means it's dry. So won't that be 4 dry days in a row, right? 1 every year, right? So she got lucky. Every single time she got dry, 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 and dry. Now, the multiplication rule says that if you want to do this particular one, you can multiply each one together separately. And that's 0.77. To look like that guy. And on my calculator, why don't I just do that guy? Because you get it, it's a little bit quicker, since it's the same number. So 0.77 to the power of 4, and I get the answer 0.3. What did it want accuracy here? 3 decimal places, so 351. And then in question C, what's the probability that it will rain on her parade at least once? So I'll just say at least 1, right? It's going to be R. Isn't this guy and this guy, aren't they complements? Right, at least 1 day it rain is the exact opposite of all 4 days being dry. And so won't the answer just be 0.649? I don't need to multiply anything together. I don't need to do some weird calculations. I can use this result to find that result. So that's an example of one of those at least 1 situations. Are we good with that? Right. See if I can find one more of these things. They're hard to find. Here we go. This is question 17. In question 17, suppose the chances that you win in a casino game, maybe it's blackjack, is 0.4. And you play 4 games. What's the probability of winning at least once? So the probability of winning at least once. Let me rewrite that again. Probability of winning at least once. Now we have to figure out what the complement of winning at least once is. What's the exact opposite of winning at least once?
Losing every time.
Okay, and they're 4 times, so it's going to be 4 losses, right? And since it's a complement, won't we be able to say 1 takeaway there? So do you see that the way I calculated this question wasn't to find out what the answer was, but to find out what its complement was and take away from 1. This is easier to calculate than that would be, right? I mean, try to think of it at least once. Well, he might have won once, but was it the first game he won, or was it the last game he won? Well, he might have won twice it, but couldn't that be? Excuse me, I should switch my phone off. Go away. So where was it? Right, so the complement of winning at least once becomes losing all the time. So we're going to get that. Now, to be able to get that, don't I need to know the probability of losing? What number is the probability of losing in this story?
0.6.
Because it's a complement. So our answer is going to be 1. Take away. Can I save some time and just do that so I don't need to write all the multiplications down? No, lose, 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 lose. That's 4 times in a row. And on our calculator then, 1 take away 0.6 to the power of 4 ends up being 0.8704. And what do they want the answer to be? Oh, they don't want it rounded off, so the entire answer. Aren't we using the at least once, but using it in a slightly different way? Don't we normally get this and we try and find that? But you can, sometimes you're given that to find, in which case you do it the other way around, right? It's like a seesaw, right? One end or the other, it doesn't matter. If you know one, can't you figure out the other? Are we good? Right. Last one of this type, and then I'll go back to some of the earlier questions. Again, it's going to have an at least one. This waitress, the chances that she gets a big tip. And a big tip for her is anything that's more than 20% is 0.26. Right. So if she goes to any table, you know, that she waits on, there's a 0.26 chance she's going to get a big tip. That's nice to know. And it's independent of the next customer. They just do it to qualify. And she's going to do 5 tables. And we're being asked to find what's the probability that she gets at least one big tip, right, out of 5. So it's kind of like this question, isn't it? We're being asked to find the at least one guy. So I'm going to do 1 takeaway, the opposite of that. Okay, what's the opposite of not getting at least one big tip?
Was it 0.74?
It is going to be connected to that point. So shall I call that a small tip? Just give it a name. And that is 0.74. Now she's doing it 5 tables, right? So won't the chances be a small tip on every single one of the 5 tables, right? So it's going to be small, 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 right? It's a bad night. 1 takeaway 0.74 to the power of 5. And on our calculator then, 1 takeaway 0.74 to the power of 5. We are talking about, what did I want this time? 4 decimal places. So 0.7781. Or as a percentage, about 78.81% if you want to imagine it a little bit better. So she's probably going to find more often than not, she's going to get at least one big tip, right? Every 5 tables. You're probably going to get one, right? 3 or 4 times anyway, that's going to happen. So it's not a bad average. Are we comfortable with the at least one type question where you do some repeatedly and you're either asked to find at least one or you use it? So we did here. Now working back with should we talk about here? Let's look at what's called a probability tree. There we go. And the probability tree is a visual way of calculating complicated probabilities involve two things or more than one thing happening, right? So let's suppose that we do, what should we do? Let's do that the probability that it rains is 0.7 and the probability that it's dry then is 0.3, right? We're making the world that can only be rainy or dry. And we are going to look at rain, dry. We're going to look at 2 consecutive days of weather. And a probability tree looks like that. I guess it gets its name. If you do it that way, doesn't it look like a tree and it branches out? Now, the way this works is, this is the first day, right? And this represents the second day. And on the first day, the chances that it rains is 0.7. And the chances that it's dry is 0.3. On the second day, the chance that it rains is 0.7. And on the second day, the chances that it's dry is 0.3. Have you noticed that it's always 0.7 and 0.3 in this story? Now, from this tree, you can actually get probabilities to certain events. For instance, what's the probability that it's one dry day and one rainy day? Suppose I'd like to know, what's the chances over the weekend? Let's say this is a Saturday, Sunday. What's the chances over the weekend that I get a one dry and one rainy day? Now, what you do in these diagrams then is you look at the 4 destinations because they represent all the things that could happen over that 2-day period. Now, if you're talking one dry and one rainy, would you agree that that guy there represents that event? Isn't it a rainy day and then a dry day? Is there any other one of the 3 that's left that would also correspond to one dry and one rainy day? Agreed? Where is it?
The one dry below.
That one? Agreed. Now, these 2 correspond to this event. So let's see, how do I find the probability of this one? Well, what you do in a probability tree is that you follow the road that leads you to there. And you see that this road is a 0.7 for the first day and then a 0.3 for the other day. So this would be 0.7 multiplied by 0.3. So the chances of that particular combination happening is 0.21. Well, let's look at the second one. Would you see the second one, it goes 0.3 and then followed by 0.7. And that also ends up being 0.21. What do you think I do with these 2 probabilities then to find this one?
You add them together?
You do.
You
And so there is a 42% chance that during the weekend I'll get a dry and a rainy day, right? I'll get one of each. Now, if you do the 2 rainy days, which would be that one, would you agree that's rainy day and another rainy day? That's going to happen 0.49 of the time. You agree? And we might get really lucky. And couldn't we have a dry day and then another dry day? And when we take that one into account, we get 0.3 times 0.3, which ends up being 0.09. What do you think these 4 probabilities add up to, or should add up to?
1.
And if they don't, you've screwed up your tree. So that's how you check your tree. once you've found all the ends, right, all the destinations and calculated them, they should add up to 1. If they don't, then go looking for a mistake. So far, so good. Can you see how that tree diagram could be useful when you get messier situations? Right. So I'm now going to do a probability tree with 3 children. There's a question in the homework that's like this, but not as big. And I'm going to make my life a little bit easier by keeping the numbers simple. Can we have the probability of a boy is 0.6 and the probability of a girl is 0.4? I know that's quite inaccurate, but I don't want to make them both 0.5 because then you'll not know which one came from which, right? So I got a 0.6 and 0.4, and we're going to have a 3-child family. So we'll start off, as you'd expect, with a boy and a girl. And the boy is going to be 0.6 and the girl is going to have a chance of 0.4. And that's the first child in the family. And then you do the second child. And you go boy, girl, boy, girl. And it's still 0.6, 0.4, 0.6, 0.4. And one more time. Can you see that this tree diagram has physical limitations? Would you agree you wouldn't want to do it for 5 children? Right. So it's useful for small numbers, not really practical once it gets too big. But to complete this question, it's a boy, girl, boy, girl, boy, boy, finally a girl. And it's 0.6, 0.4, 0.6, 0.4, 0.6, 0.4, 0.6, 0.4. Now, I'm not going to calculate every single one of these. There's 8 of them altogether, right? But let's do a couple of questions. What's the probability that all 3 are boys? Well, if you're going to be all 3 as boys, would you agree it's this one up here? Is it the top one the only way you can have 3 boys, right? A boy, and a boy. And that ends up being 0.6, 0.6, 0.6. And the chances of getting a boy then are 0.216. About 21, 22% of the time, if this was true, you'd have families with 3 boys. Now I'm going to ask a difficult or an awkward question. You have more boys than girls. Now, if you did not have this picture in front of you, I think you'd be hard pressed to find the answer to this probability, right? I mean, where do you even start? Well, on this diagram, there's 8 destinations here. Some of them are more boys than girls, agreed? So all the boys count, right? So I'm going to use that number. 2 boys and a girl, so I'm going to use that one, agreed? Right, that's a boy, and a girl, that counts. A boy, a girl, and a boy, that wins. A boy, a girl, and a girl, so I don't count that one. A girl, a boy, and a boy, that one wins. A girl, a boy, and a girl, that one doesn't. A girl, and a boy, that one doesn't. And a girl, and a girl, that one doesn't. So it looks like we've got those 4 guys, right? The green one and the other 3. Would you agree those are the situations that end up being more boys in the family than girls? And this one is made up of, let's say, 0.6, 0.6, 0.4. This one is 0.6, 0.4, 0.6. And this end one is 0.4, 0.6, 0.6. And I'll do those guys and see what we get. 0.4, 0.6, 0.6, and we get 0.144. Actually, we get 0.144 for all of them. So if you want to know what's the probability that you get more boys than girls, don't you just add up all of them being boys, and then these other three situations where there were 2 boys and 1 girl. 4, 8, 12, 18, 5, 9, 13, 14, 2, 3, 4, 5, 6. Or about 64.8% of the time. Have I sold you on tree diagrams are useful for complicated probability questions? Now, if the question had just been all 3 are boys, couldn't you have just did boy, 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 and just multiplied these together and got the answer? So I wouldn't need a tree diagram for the top question, agreed? And I wouldn't need the tree diagram if at least one of them was a girl, because wouldn't it just be the complement of this event? But all the other combinations, would you agree you really need a table because there's, which ones of these 8 are you talking about? That kind of question, it comes through. Are we okay with that question now? Before we move on then, I want to talk a little bit about my family, because it came to me. I have lots of sisters. One of my sisters is Morag. She always wanted a girl. And she got 4 boys and gave up. Right? I think she would have gave up if she'd got a boy and a girl. I think if she'd got a girl, actually, if she'd got just a girl, she'd probably have given up, right? But she wanted a girl, so she kept on trying and live his life, and so she didn't get any. But just to finish this story, genetics is a weird thing. Her sons are all married now and have families. And do you know what they got?
They all have girls.
They all have girls. So you figure that one out. There's a genetic weirdness of, was it skipping a generation or something? It just happens that way. I just thought that was kind of vaguely interesting. Okay. So I'm pretty sure I've covered most of the stuff from that session. So we can move on to probability. Pardon me. Give me a few seconds to load it up and we'll get started. Has anybody got a bad joke while I'm getting myself sorted out here? Anybody got a good joke? Nothing? Last chance. Parker, you've got a joke. I can tell you've got a joke in there. No. Okay. Let's start the next section then. I'm going straight to the homework. And don't talk yourself out of the obvious answer here. A lot of these early questions are going to be pretty straightforward. I just want to get a quick intro to it, and then I'll talk about what's called relative frequency and how that's connected to probability. So here we go. In each of the following, which are legitimate values for a probability, and explain why if it's a no. Is 0.75 a possible number that you could get in a probability? Yeah. And so your answer is yes. See, don't overthink it. Is 0 a possible answer for a probability? Yeah. Doesn't that just mean it ain't going to happen, whatever it is they're talking about? Is 1.4 And now you have to choose which of the three no's is the reason why 1.4 is no good. You, Barbara's pointing at that one. Is that right? The probability cannot be greater than 1. Is that the one you meant? Good, because that's the right answer. What about 1.00? 1, essentially, right? Yes. What about, oops, wrong yes. I meant to put a yes here. Don't know what answer I'm going to put in that. I'll fix it in a minute. What about 1.01? Could that be a probability? No.
Yes.
No. Probabilities can only be between 0 and 1. They're not even allowed to be a tiny bit more than 1. And they're definitely not allowed to be negative. Which brings me to the no one, which is E. And that's the dot I should have picked, isn't it? Would you agree they're pretty straightforward questions, right? Here's a number, can you get it? I think it would have been nice if they chucked in a couple of fractions and percentages as well, you know, just to, you know, mix and match it. So let me add a pretend question or two. Could 82% be an okay probability? 82%. Yeah. 103%.
No.
7/8. Is that okay as a fraction? 8/7. Right. So if it's going to be a percentage, doesn't have to be between 0 and 100. If it's going to be a fraction, it has to be between 0 and 1. If it's going to be a decimal, it has to be between 0 and 1. And that's pretty much it. So I'm now going to talk about, if I can find the right button. Okay, where are you hiding? There we go. Let's talk about relative frequency and their connection to probabilities. So I want you to imagine that we collected a sample and we asked people something pretty mundane. We went and asked them, what was their favorite drink, right? Non-alcoholic. And so the answers that we got were Coke, Pepsi, Dr. Pepper, and to make my life simple, none. I don't like any of them. I don't drink carbonated drinks, right? And we have two columns, one that we're pretty familiar with, which is frequency. And that really just is how many people said they like it. So 120 like Coke, 90 like Pepsi, 60 liked Dr. Pepper. I'm trying to make this number nice. And 30 didn't like any. Now the next column is a guy called relative frequency. Before I talk about that, the total number of people in this sample was 300, right? How do you calculate relative frequencies? So what's the relative frequency for people who said Coca-Cola?
Just opposite, so it would be 180.
No, I know where you're going. You're thinking complementary.
Yeah,
Yeah, no, relative frequency is a different thing.
Would it be 120 over 300?
Yes, it would be. Can you remember, I know it's a while back, but you remember when we did some frequency tables, one of the tables was called relative frequency. So it's 120 over 300. We typically make these things decimals. So that's 0.4. This one's 0.3. Not sure what that one is. I think it's 0.2, but let me double check. Good, it is 0.2. And lastly, 0.1. And these are called relative frequencies. If you do these calculations correctly, roughly, because sometimes rounding off causes issues, what should all the relative frequencies add up to?
One.
Agree. Now, you got to be a bit generous with yourself. Do you know that these ones came out perfect, but can you imagine sometimes where you have to round everything off to 2 decimal places? So you might get 0.99 or 1.02. And that's normally okay. That just means, you know, some of the numbers get rounded up and not many get rounded down, right? And that just happens. But I mean, if you add it up and it's 0.8, right, you're wrong, right? Something's not right somewhere. Or if you get 1.5, you're wrong. So you can use this as a check. Now, how does relative frequency interact with what we call probability? Well, you get questions that say something like this. You choose one person at random. From the sample, in this case, 300. So it's going to begin with, you choose one person at random from the sample of 300, and they ask you, what's the probability that that person actually said they preferred Coca-Cola? What do you think that probability is going to be?
.4.
Yeah. So in other words, isn't the relative frequency in this context the same thing as the probability of you picking one person from that sample and getting that answer? So the probability that they like Dr. Pepper, won't that be 0.2? And the probability that the one person you chose didn't like any of them, wouldn't that be 0.1? So do you see that these relative frequencies allow you to answer this type of question where you just choose one person from the sample and you're interested in what they're doing? For instance, I should be able to do this one as well. What's the probability I choose one person from the sample and they like Coke or Pepsi? What would that be? They like Coke or Pepsi. What's the probability of that being chosen?
0.7.
And isn't that the people who like Coke plus the people who like Pepsi? 0.7. What's the probability that you pick people who don't like Pepsi for whatever reason? They don't like Pepsi. Who is that?
0.7.
Okay, where did it come from? You're right, Brendan.
1 minus the relative frequency of Pepsi.
And in this case, 0.3 gets you 0.7. And that's the way I would do it, but couldn't you just add up the other 3 and get 0.7 as well? But that's the way I would think of that. So can't relative frequency be used, these sample tables, right, with relative frequency, can't they be used to answer what's the probability that if you choose one person, a certain thing is true? I would go with that. Now, there are going to be, coming up shortly, some examples of relative frequencies being used for probabilities. And then there's going to be, I'll try to find the right phrase that they use so I don't kind of give you another word. And you're going to look at how probabilities are calculated. And the choices are, did they use relative frequency? So that would be you collected a sample and you made a table. That would be a relative frequency. Or what they are calling, and that's why I had to look it up, personal. Let's do an example. If you ask your pal and they say, it's a 40% chance that it rains tomorrow, they're just probably giving you their personal opinion, right? They're not basing it on any real facts, just a gut feeling, right? So if your friend went and said, it's a 40% chance of raining tomorrow, that would be it. Now, if a weatherman said there's a 40% chance of raining tomorrow, didn't they probably collect lots of data and put it into some kind of table, and how many times did it rain, you know, when this particular weather situation was happening, right? That would have almost certainly came from numbers, right? From data, relative frequency or otherwise, in which case you put it into that category, right? Suppose I, suppose your sister-in-law said, there's a 90% chance that you're going to get divorced. Well, apart from falling out with her, I hope, you would say, well, how come you think that? Well, I just don't think he's the right one for you or something, right? But isn't that a personal judgment call? You just put a number on it to kind of make it seem, I don't know, more realistic. Could she say, look, there's a 1% chance you're getting divorced, or a 99% chance? Aren't they just numbers to try and emphasize a belief, right? Those are all personal. They're just made up, gut feeling, whatever. Relative frequency, there was data behind it. So keep that kind of in mind when we do some of these later questions. Now, let's see if I can find an example of that now. Right, so I'm going to nip over to the homework. And we'll have a look at a lot of reading today. Now, here is a story, and we have to decide, is it relative frequency or is it personal? And not only that, if we decide it's one or the other, we have to justify it by which reason you chose. So here's the first one. According to Krantz, which is a survey done in 1992, page 161, the probability that an American is going to be hit by lightning is 1 out of 685,000. How people figured that out? Does that look like it's a relative frequency, or do you think that's a personal opinion?
Relative frequency.
Right, it probably came from some data somewhere, right? How many people get struck by lightning divided by 330 million Americans, and then simplify it, right? So we know it's a relative frequency, so that means it's dot number 1 or it's dot number 3, right? And that's where it gets a little bit trickier between the two choices. So I'll read the first one. The relative frequency interpretation of probability applies here. We agreed on that. The probability was most likely determined by observing a large number of Americans injured by lightning during a number of years and dividing by the population. In fact, I'm going to stop reading. I think that's the one. Would you agree that seems reasonable?
Yeah, the other one says something about personal experience.
Yeah, I don't think we would use that. So if you get to the first one and you like it, you probably don't need to look at the other choice, if it's a good reason. Now, according to your neighbor, right, there's a 1 in 4 chance that our tomatoes are going to actually do any good, right? She's going to get some tomatoes, bear fruit. Personal or relative frequency?
Personal.
Yeah. I don't know where she got that quarter from. She's just her gut feeling. And you can figure out which one of the personals make more sense. Now, according to the nursery where your neighbor gets her tomatoes, The nursery says the chances that you will get, your tomato plant will live and give you, tomatoes at the end is 0.97, which is good news because you don't want to buy tomatoes if they're going to die, right? Tomato plants. What do you think that one came from? Personal or relative frequency?
Relative frequency.
Right. So he's sold thousands of them and he's noticed only a few die. I would say so. The probability that your husband will outlive your wife, and this is for American couples, is 3/10. Where do you think that comes from?
Relative?
Yeah. I'm assuming that they know married couples and then one of them dies and they know if it's a male or female or whatever, and they've got that. So I'm going to tell you my joke now because it's in my head. Why do Scottish husbands die before their wives? You're meant to say, I
Why?
don't know. Because they want to.
That's funny.
Brendan finally got that one. Abra put her hand on her head and just kind of, oh God, that was bad. Brianna, did you like that joke? Abra, what was the problem with that joke? It just was bad.
I mean, it's not a problem. It's just, yeah, it's good.
Okay. Okay, question 5 is the same kind of story, so let's just pick one. Okay, B. In a debate with your friend, she thinks that there's a 50-50 chance that God exists. Would you agree that's personal? I mean, I don't know how you could even define that information. Okay. Okay, now moving on to question 6. Casino games often use a fair dice, 6 dots in them, we all know that. When it's tossed, it's rolled, each side equally likely, we knew that. Using a physical assumption that the dice is fair, determine the probability of each of these outcomes for the number of dots showing on top after a single die roll. Do you know that's a lot of words for just saying what's the probability you get a 3 when you roll a dice? I mean, when you boil it down, isn't that what that probability is asking? Right. So, isn't there only 1 3, so it'd be 196. And they want the answer as a fraction, so I'm good. Mine doesn't do it right now, but if I clicked on that, when you get the little math thing, you can put the fraction button in, I think. What would 1 or 5 be? So don't overthink this one.
2 6.
1/3.
2 6 is correct. But wouldn't you write down 1/3 when you're finished? But normally you write down the answer, then you have a quick look at it and say, I can simplify it. What about an even number of dots? Don't overthink this.
Half.
Half. Right, so 3 6 and become a half. In a lot of ways, isn't this easier than the first one, part A? Most of the time. Well, we'll see if it continues. A computer solitaire game uses 52 card deck, randomly shuffles it. Theoretically, it should be possible to find the optimum strategy for playing and to compute the probability of winning based on this strategy. Not only would it be an extremely complicated problem, but also the probability of winning for any particular person depends on that person's skill, okay? Explain how an individual could determine their probability of winning a game. And hint, it might take you a while. Right, let's say you play blackjack, right? Abra plays blackjack. She's absolutely hopeless at the game, I've decided. She might be great.
I am hopeless at the game, it's fine.
Okay, Brendan on the other hand is a whiz-kiz at blackjack. But we'd like to put a number on that. So if we had to do an experiment and we had plenty of time, and I'd probably have to pay the two of you, wouldn't we just get you to play lots and lots of games of blackjack against the computer? because then it's fair, right? It's the same every time. So far, so good. And Abra wins 10% of the games and Brendan wins 80% of the games. Can you see that now we have data to back up that Abra's horrible at the game and Brendan's good? Right? That would be what we would, essentially you could call that a simulation, but it's a little bit more than a simulation, isn't it? More like an experiment. And what you do in experiments, or some experiments, isn't you just keep repeating the same thing over and over again, right? You play the game over and over again. If you do it if you do it lots of times, can't you get a pretty good answer to what's the chances Abra is typically going to win a game against the computer and what the chances Brendan is, right? Now, that doesn't guarantee one particular game, right? Let's suppose Abra's got a 10% chance, Brendan's got an 80. And you play just one game, and both of you are at the table, and you're both playing against the computer, right? And you want to see who's going to win. Couldn't Abra win the first game and Brendan lose the first game? Do you see, probability doesn't guarantee anything? Doesn't it just give you the chances of it happening? So you can't go in and say, oh, well, Abra is now going to play Brendan. Brendan's going to win every single time, right? If it was just you two playing against each other, no computer in it, would you agree that that's not what would happen? Wouldn't Abra win some, Brendan win some? Okay, Brendan will win more than Abra in the long term, but couldn't Abra have a great day and win the first 5 games and Brendan leaves broke? Right, could happen. So never think probability is telling you what's going to happen, for sure. It just puts a number on how likely something is to happen, and that's not the same thing.
So how would you answer that question?
Oh, we have got playing a large number of times and recording how many times they won. Are you looking at the question screen or me right now? I'm not sure where we are.
The question screen.
Okay, can you see the second dot that I've just highlighted? That would be it.
Yeah, sorry, I just didn't see that before you scrolled down.
That's fine. Now, Alicia's statistics class meets 60 times during the semester, right? So I guess it's 60 days, right? It's 12 weeks semester, seems right. And each time it meets, the probability that she will be called on to answer a question is 1 out of 60. Ah, that's not that big. Does this mean that Alicia will be called on to answer the first question exactly once during the semester? No. So, no. This does not mean that she will be called to answer the first question exactly during. The probability given the proportion of times the event occurs over the long run. There are 60 classes, and our probability of being called to answer the first question is 1/60th. She may or may not be asked on the first question. Right? In fact, theoretically, couldn't Alicia be asked in every single one of the days that she turned up? Highly unlikely, but it could happen. Could she also never be asked? But in the kind of vagueness of, in general, she's got a 1 in 60 chance. And in 60 days, that probably means she's probably going to be asked once, but only in a very vague way. This is a lottery one, very similar, so I'm skipping by that one. And let me do this one. Well, I can actually do this one on the screen. I was going to do it on paper, but I don't need to. This table shows the investigations of the incidence of myopia. Sure, is myopia? I don't know. I've heard that term, but I'm not sure. Is that short-sightedness? Anybody know? Okay, we'll just call it myopia then. The incidence of myopia later in childhood of children that slept in the darkness in early childhood. So what is the probability that a randomly selected child would develop some degree of myopia? Oh. some degree of myopia would be 18 plus 2, which is 20, out of 178. So based on this data, 20 had some kind of whatever myopia is.
It's a nearsightedness.
Oh, I was kind of closer. Right, it would be that. Enter your answer as a fraction. I don't know off the top of my head, at least I don't want to try and figure out in case I screw up. So I'm typing it into the calculator right now, and I'm doing that math button trick, and it's 10/89. You remember style points, make it as simple as you can when it's a fraction. I'm sure I've shown you. Haven't I shown you how to make calculators turn things into decimals? So you know what to do in that arms. Okay. Time to move back to the notes now. And white screen. So 2 events, let's call them A and B, are mutually exclusive if they have no terms in common. So 2 things are mutually exclusive, right, if they don't have any terms in common, right? They share nothing in common. So let's do cards because they're the easiest ones to generate that. Would you agree that if event A was hearts and event B was getting black cards, that they are mutually exclusive? Would you agree they share nothing in common, right? So these 2 things are mutually exclusive. Now, how about hearts and event B is kings? Why are they not mutually exclusive?
Because there can be hearts that are kings and vice versa.
Right, there is, for instance, isn't there a king of hearts that belongs to both? Right. Now, why is that important? Well, when you are calculating the probability of 2 events together, right? So suppose one went and asked us, let's do that. I'll call this question 1, and then I'll call this question 2. In question 1, if I asked you, what's the probability that you got a heart or a black card? Okay, so that's going to be a heart or a black card. Couldn't you just take the number of hearts, which is 13 out of 52, add it to the number of black, which is 26 out of 52, and get the answer 39 out of 52, which is what, 3/4. Does that seem reasonable? When they are mutually exclusive and you want to do an OR story, don't you basically just add the 2 things together? So if they are mutually exclusive, which they are, you can find the probability of an OR by adding them together. Now, if the 2 events are not mutually exclusive, the probability of A or B is more complicated. So let's do this one. What's the probability that you get a heart or a king? Right. Normally I do them all on one big 52, but we'll separate it out. There are 13 hearts. There are 4 kings. But we're double dipping here, aren't we? Aren't we counting one of the cards twice? Agreed? And so we take away the extra one, right? The one that we double dipped. And so if you did this one, it would be 13, add 4, that's 17. You'd get 16 out of 52, which I believe is 4/13. Now, what did that look like as a probability? When they're not mutually exclusive, it's the probability of A plus the probability of B, and then you take away the probability of both, and both is called AND. Right, so if I went and said to you, what's the probability that you're a king and a heart? Wouldn't the answer be 1 card out of 52? You see where the AND is coming from. So when you are calculating ORs, question where it's A or B. If they're mutually exclusive, just add them together and you're good. If it's not mutually exclusive, add them together and then subtract the both, right? So let me try another one with a little bit more in it. That's the probability that you get a club or a face card. First thing we're going to have to decide here, are clubs and face cards mutually exclusive events?
No.
Agreed. Would you agree that they share a lot of terms, don't they? In this case, quite a few. So if I was going to separate that out, and I'll do it without A's and B's, it's the probability of a club plus the probability that you get a face card, take away the probability of a club and a face card. Or if you want to say it for short, that you get both. Now, I know how many clubs there are. There are 13 out of 52. Great. And I know how many face cards there are. Hopefully you can remember, isn't there 3 from the diamonds, the clubs, the hearts, and the spades? So there's 12 of those. Now, what's the chance that you get a club and a face card? Out of the 52 cards in a deck, how many are club face cards or face cards that are clubs?
3.
So do you see that the double dipping here is 3? Right. So what you would get when you combine these is what, 22 over 52, and I believe that's 11 out of 26. Are you comfortable with why mutually exclusive is important when you want to calculate OR probabilities? If they've nothing in common, just add them and call it good. And those ones are dead easy, right? It's the not mutually exclusive questions that you have to figure out the double dipping. So let me now move on away from mutually exclusive and talk about another property that is used in probability. It's called conditional probabilities. And they're written typically like this. And you read this out loud as the probability of A given that B has happened. So we're going to find the probability of something happening given an extra piece of information. So somebody's going to tell you this thing B has already happened, and that is going to affect in some way or other the probability of A. So let's do the probability that you get a heart. And that's just a normal, easy probability. Would you agree it's 12 out of 52? 13, I should say, out of 52. Would you agree that's a quarter? Suppose I ask you to get the probability that it's a heart, given that it was a red card. So somehow or other, somebody whispered, oh, I caught a glimpse of it, it was red. And you think, oh, okay. What's the probability that you're now going to get a heart? Well, since you know it's a red, doesn't that mean it can only be one of 26 cards? Agreed? It's a red
Would
card. It's
It would be
one.
a half chance then.
It
right?
is, yeah, because there's still 13 hearts and now it's a half. Do you see that that piece of information hasn't it upped your chances of getting a heart? Isn't it a bit like cheating and sneaking at somebody's cards? Maybe you don't get to see a lot of it, but you at least get to see if it's red or something. Doesn't that give you a little bit more information to base probabilities on? Now, not all information is good information. What's the probability that it's a heart, given that it was a black card? Oh, well, since I know it's definitely a black card, there's 26. How many of those black cards are hearts?
0.
In this case, hasn't that basically destroyed your chance of getting a heart? What about this conditional probability? What's the probability of getting a heart given that it was a face card? Now, when they tell you, whatever it is they tell you, isn't that the bottom number? So in this case, face cards. And you say, okay, in a normal deck, there's 12 of those face cards. How many of those face cards are heart face cards? How many of those 12 are hearts? 3.
6.
Only 3. Red is 6, but hearts is only 3.
Oh, okay. Sorry.
Oh, that's fine. And hey, oh, that one's quite interesting. Isn't that the same answer you would have got if you just were told nothing? So if someone tells you it's a face card, that doesn't help the probability of being a heart. Isn't it a bit like telling you it's Tuesday? Okay, it's Tuesday, but it doesn't help the probability. So conditional probabilities, can't they make things bigger, less, or not change them at all? Doesn't depend on what you get told and what you're being asked to find. Sneaky. Different kind of probability. So I'm now going to do a tree diagram using conditional probability. And before we do the tree diagram, we're going to do this idea. It's called with replacement and without replacement, because they affect the net result. So I'm going to have in my story a bag, and in this bag there's going to be 3 red beads and there are going to be 4 blue beads. Okay, and I am going to play a little. Okay, this is a 9. That's better. I'm going to take 2 beads out of this bag. Now, when you do it with replacement, you go, you stick your hand in the bag, you pull it out and you say, oh, it's blue. And you mark down it was blue. But you put it back in the bag, give it a good shake, and then you stick your hand back in the bag and you take out the second bead, right? Because it went back in the bag, we call that with replacement. Now, the second situation that I'm going to do after that is a without replacement. We're still going to take 2 out the bag. First time in, bring it out, and whatever it is, write down what it is, but put it on the table. Do you see that the bag now is different? It's not being replaced. It's being, if you like, used up. That makes a difference. So we're going to find probabilities using a tree diagram, picking out 2 beats. So the first one is going to be, as I said, with replacement. So we'll start off, and it could be red or it could be blue. And the chances that you get a red, would you agree it's 3 out of 7? And the chances that the next one, the first one, is blue, isn't that a 4 out of 7? Does that seem reasonable? 3 out of 7 red, 4 out of 7 chance it's a blue. If you then go to the second one, it could be red. And if it's a red, it's going to be 3/7. That's a chance. Or it might be blue. And isn't the blue still going to be 4/7? So when you do with replacement, doesn't the probability stay the same every single time? I'm not going to do it, but if I did a third bead, wouldn't it still be 3/7, 4/7, 3/7, 4/7 all the way down, right? Now that's the tree diagram created. Now we can be asking all sorts of questions. I'm just going to ask 2 questions. First one is, what's the probability that both of them are red? Would you agree it's that guy there? Right, red and red, you agree? And how do we do that? We do 3/7 times 3/7, and I get 9 out of 49. So the answer to this one is 9 out of 49. And for my second probability, it's 1 of each. Right, now, if you're going to get 1 of each, right, that's 1 red and 1 blue, right? You get 1 of each. Won't that one qualify as a red and a blue? Is there another one in that list that also would be a red and a blue? What other combination would give you a red and a blue? Who cares which order it is? Because I don't.
The one with the blue and a red?
Yeah, agreed. These 2 are the 2 situations that generate 1 of each color. Order doesn't matter in this story. So I'll keep it red. So it's going to be 3/7 times 4/7, which is 12/49. And then it's going to be 4/7 times 3/7, which is 12/49. And don't you just add these 2 together? And I'll just do that in my head. And you get 24/49. So that's what the story looks like. If you wanted to know what's the chances that both were red or 1 of each. Now we're going to do the last one for today, without replacement. Same bag, same story, apart from that. Let's see what happens. The first bead comes out the bag, and nothing too strange happens. It's still got a 4 out of 7 chance of being blue and a 3 out of 7 chance being red. Now it gets decidedly different. Its first bead was a red, but it never went back in the bag. Right. First one is red, okay? Hopefully that won't go off in the next 5 minutes. First one is red. Doesn't that mean the bag now looks like that? You see there are only 6 beads in it. So what's the probability now of getting a red?
1/3.
Okay, and you're quite right. I'm just going to call it 2/6, only just to make the numbers a little bit easier, but you're right, it's a third. What's the chances of getting the blue one? So 2/6 What's the blue coming out?
Or
Four.
6.
4, 6. Have you seen that without replacement changes the probabilities? Now, let's go down here. Oh, the first one was a blue, so hasn't the story now changed into that? 3 of each. And in that case, you see that this would be 3 out of 6, which is a half, you're right, if you're thinking that, and that's 3, 6. Now, we're going to calculate the same two probabilities. The chances that both are red is 3/7 times 2, 6, which is 6 over 42, which is 1/6. Quite different from 1/7. Did you all catch that deliberate mistake? 1/7. It's what's that look like? Now you can't simplify that. So different, agreed? Not the same. Now, 1 of each, that will correspond to these two guys again. So it's going to be 3/7 times 4, 6, which is 12 out of 42, which is, I think, 2/7, but you'll keep me right if I'm wrong. And that's going to be 4/7 times 3, 6, which is also 12 out of 42. So that's going to be 2/7. So that's going to be 4/7. Let me make that one a little bit near. In which of these two situations is it easier to get 2 reds? With or without replacement? I guess it's which one of those two fractions is the biggest, isn't it? So if I turn them into decimals, 9 divided by 49 is roughly 0.184, and 1 divided by 7 is roughly 0.143. Would you agree that this is more likely? Does that make sense that if you keep the reds in the bag, they're more likely to get 2 of them than if you use them up? Now, 1 of each, 24 divided by 49 is roughly 0.490 if you round it off, and 4/7 is roughly 0.571. Oh, that's interesting. Why would it be more likely to get 1 of each if you do without replacement than it is if you do with replacement? Do you agree? This is more likely than that. Why would that happen? If you use up one of the colors, doesn't that leave proportional wise more of the other colors to come out? So it gives you a chance of the other one being different a little bit more. That's essentially what it is.